Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have discussed about how to calculate the CRR to check the cyclic softening behavior of clay-like soils, and I have discussed how to calculate the correction factor K alpha, then the magnitude scaling factors or magnitude correction factors. Now, today I will discuss that what is the effect of foundation load on CSR. Okay, so I will discuss that part, that effect of foundation load. Okay, so that means we are calculating it for CSR. So this is, I see CSR means it is tau average. Okay, so this is we are talking about tau average divided by sigma V0 dash or sigma V dash. So our expression of the CSR, that is 0.65 and A max plus G, then sigma V or V0, that is for soil, into RD and divided by sigma V0 dash. So that is contribution due to the soil only. So this is the soil column that we have considered. Now we will add the surcharge or foundation load. So that means here plus K and del sigma V, that is for building or the foundation Now that is divided by sigma V0 dash. So that means this additional component is being considered due to the additional stress that is coming on a foundation base due to a building. Okay, so that where K can be taken as 0.2, and how I will calculate del V? So del V or del sigma V I can calculate if this is your Q net that is applied at the foundation base. So suppose this is your foundation, now at the base which is applied is the Q net. Then the stress will be distributed from the base of the soil. Suppose this is your ground level, from the base of the soil, and that distribution is 1:2 distribution. That generally we consider during the design. So 1:2 distribution, and it is same for both the sides. Okay, so that means 1:2 means 2 depth, 1 in the horizontal direction. So 1:2 distribution. So then you will get that your at any depth z, what is the del sigma v at any depth z from the base of the foundation. Okay. So Q net acting as the base. So this will be into BL if it is strip by your rectangular footing by B plus Z into L plus Z. So I will get that. So from here, if it is Z, so this will be Z by 2. Horizontal, if vertical is Z, horizontal will be Z by 2. Here also, if it is vertical height is Z, horizontal length will be Z by 2. So overall it will be, if it is B, then at this Z depth, this is actually Z by 2. This one is also Z by 2. It will be B plus Z by 2 plus Z by 2, that will be B plus Z. Similarly, other direction, if it is a rectangular footing, so this is for rectangular area or footing, and it will be del sigma V will be simple Q net into B divided by B plus Z. It is for a strip footing. Clear? So this way I can calculate the CSR if I consider the effect of foundation load. Now if it is at the base, then your Z is 0. So it will be del sigma V will be equal to Q net, the net stress acting at the foundation base. Okay. Now here for the foundation, how to estimate the, because if it is a foundation load, then because of this presence of this foundation, this static shear stress will be will present. Okay, static shear stress will present. Now how to calculate that static shear stress due to the presence of this foundation load? Then you apply the K alpha, because till now I have not solved any problem where I can calculate the K alpha. So now in the next part I will solve one numerical problem and I will show you how I can calculate the K alpha. So right now I am giving the expression, because now if it is foundation load is there, because of this the shear stress will exist, or if it is sloping ground, there also shear stress will exist, static shear stress. Okay. So now estimation of the K alpha. Or estimating of K alpha under this foundation load. So we know that factor of safety, or F, if I say F is the factor of safety, which is factor of safety, that is equal to your shear strength divided by shear stress. Yes or no? Okay. So I can write for clay. So you know that the strength, shear strength expression, this is what? Cu plus sigma V dash into tan phi. This is shear strength expression. Now for clay like soil under undrained condition, that this will be phi equal to be 0. Okay, so that means it is undrained shear strength. Cu is basically, it will be ACU, undrained shear strength of the soil. So or the tau strength will be Cu, which is basically undrained shear strength. So factor of safety will be your ACU divided by the static shear stress that is developed. So SU is the undrained shear strength for clay like soil, and divided by ST is the static shear stress. So this is your shear stress. Okay, and SU is the undrained shear strength of the soil, because your phi is equal to 0, so this part will be 0. Cu will be tau strength, and tau strength for clays is SU. SU is the undrained shear strength, which is, that means here your SU is same as tau strength. So SU will be equal to Cu. So that means this is my strength divided by stress. So strength is SU divided by ST. So now if this is the your shear stress, now the what is the expression of your T alpha, your expression of K alpha? Here you can see it is ST divided by SU. ST divided by SU. So that expression you can write that my alpha or ST divided by SU is equal to actually 1 by F, 1 by factor of safety. Now for foundation, how can you get the factor of safety? That is the question. Now you know that factor of safety for static, factor of safety of foundation can be determined for CNC or CUNC or SUNC, then SC, DC if it is not inclined. So then NQ, gamma DF, SQ, DQ plus half gamma B, N gamma, S gamma, D gamma minus gamma DF. This is the Q net divided by the net stress which is acting. That is the foundation factor of safety for any foundation. Okay. So first, whether it is a sand or clay, you calculate the factor of safety. So you calculate the net load carrying capacity of that foundation, divided the amount of actually stress acting on the base, then you will get the factor of safety. Now if you take 1 by F, then you will get the ST by SU. That ST by SU you can put here. That ST by SU we can put here to calculate the K alpha. Or if you want to calculate the alpha for clay like soil, alpha how will calculate? So you know that alpha will be equal to your tau ST divided by sigma V0 dash. So I know that my tau ST divided by SU, that is equal to 1 by F. So that I can write that tau ST divided by sigma 0 dash into sigma V dash by SU. So this is equal to alpha. Alpha sigma V dash by SU. So I can write that alpha will be equal to one by F into SV sigma SU sigma V0 dash. So this way I can calculate the alpha also. Okay, but here the alpha calculation for normally consolidated clay, that alpha calculation is not required. Even for over consolidated clay also, yeah, alpha calculation is required in here. So this way I can calculate the alpha. Okay, it is clear that alpha is tau. I know that tau st by SU is 1 by f, and that is for clay like soil, and alpha is equal to tau st divided by sigma v0 dash. Now tau st sigma v0 dash I can write, oh sorry, this is so this tau st by SU is 1 by f. Now this tau st by SU I can write tau st by sigma v0 dash into sigma v0 dash divided by SU. Now this is alpha, so this will be equal to alpha into sigma v0 dash into SU. So if this is my 1 by f, this is my 1 by f, so alpha will be 1 by f into SU divided by sigma v0 dash. So if I know the SU or Cu value, 100 shear strength of the soil at any depth, and if I know the unit weight, I will get the your sigma v0 dash also, then I will get the alpha value. Clear? But how I will get the F? F I will get the foundation, I will calculate the net ultimate bearing capacity divided by the stress that is coming at the foundation base. We will get the factor of safety of the soil. That factor of safety I will use it here. Now this technique I have discussed for clay like soil, that can be used for sand like soil during liquefaction check. So in that case, what will be your, this is for your clay like soil. And one more thing that I want to discuss, that here, so factor of safety for static, that will be, if I take that your for phi equal to 0, so your this part, third part will be 0, this part will be only gamma df, and this gamma df will cancel. Only if phi equal to 0, it will be simply 5.14 or NC, if I take 5.14 say, and SU or CU, and I am taking only SC, DC value is 1. So that means you can calculate you can consider that these are the safe factor, depth factor, inclination factor, you know there are other factors. So you can go through any foundation engineering book and you will get how to determine the bearing capacity of a foundation. So for clay soil or sandy soil, okay. So that you use here, basically you calculate the net ultimate bearing capacity of the soil or the foundation, then divide it by Q net. Okay. Now for strip footing, my SC, that means the shape factor is 1, and for square footing, S is 1.2 and DC is 1. Okay. Now this is for static factor of safety. Now the seismic factor of safety is less than the static factor of safety. So for seismic, generally that is static divided by 1.3, or seismic factor of safety is 0.75 times of the static factor of safety. Why we take the lower factor of safety in the seismic? Because it is confirmed that the static load will come, but there is no confirmation that the seismic load under which I am designing will come or not. That's why we reduce the seismic factor of safety, and it is taken by 0.75 times of static factor of safety. So that means here the factor of safety I am talking about, na, this factor of safety when you calculate the alpha. So that factor of safety should be the seismic factor of safety you have to consider. So this should be the seismic factor of safety. Remember, first you calculate the static factor of safety by calculating the net ultimate bearing capacity based on the whether it is soil, is sand or clay. Then divide it, it's the net stress that is coming at the foundation base. Then that will be your static factor of safety divided by 1.3. You will get the seismic factor of safety. That you will use to calculate the alpha. Okay. So now this is for clay like soil. A similar way for sand like soil, soils I can use that factor of safety is what? Strength. And for sand like soils you consider that SU or CU is equal to 0. Okay. So it will be sigma V0 dash into tan phi divided by static shear stress. Okay. And now my alpha is equal to ST divided by sigma V0 dash. So that alpha I can calculate alpha as a, so this is alpha will be your tan phi divided by factor of safety, which is seismic. So this way you can calculate the alpha value. Okay. Yeah. So this way you can calculate the alpha value. Once you calculate the alpha value, now you use these charts. You know the alpha value. If you know the N160 value, you will get the K alpha using these charts. And from the clay, if you know the ST divided by SU, that is 1 by F. So you put it here, 1 by F, you will get the K alpha. Or you can calculate the alpha value, then you can use this expression, this alpha, and you will get it. And here I have given that your this is alpha into SU by sigma V dash. That also you can convert by SU sigma V dash, which is this SU sigma V dash can be converted by using these expressions also. Can be converted. Okay. So, or you can directly calculate the alpha and then you will get the K alpha, or you can SU by sigma V dash you can convert by using these expression that I have done here, and then also you can calculate the K alpha. Clear? So these are the different methods by which, so that means this expression is for this expression to calculate the alpha, this expression that I have given, it is for OCR equal to 1. For this is for normally consolidated clay. For over consolidated clay, you have to convert these SU, you have to convert this, here you can see SU by sigma V dash, SU by sigma V dash as 0.22 OCR to the power 0.8, 0.22 OCR to the power 0.8 to calculate the alpha value. Clear? For normally consolidated clay, you can use this expression. For over consolidated clay, you have to convert it to 0.22 OCR 0.8. And then you will get, so this will be that now, this will be 0.22 OCR to the power 0.8 divided by F. That is equal to your alpha. Clear? So now this way you can calculate the alpha, and from there you can calculate the K alpha. Okay? And this technique you can use for this effect of foundation load to calculate, and the estimation of K alpha for clay like soil as well as sand like soil. So, this is CSR calculation is common for clay like soil and the sand like soil, and for estimation of K alpha is slightly different for sand like soil and clay like soil. If it is a combination of both, okay, then you know how to calculate it. This strength, then there will be Cu and sigma V dash tan alpha both will present. But as we are discussing this clay or sand, then we are taking Su is 0 for one case and phi is 0 for another case. If they both are present, then you have to consider both. Okay. So now this way, so first you calculate the static factor of safety. From there you calculate the seismic factor of safety, and that factor of safety used to calculate the alpha value. And there are expressions, number of expressions are available to calculate the factor of safety, static factor of safety under foundation load for sand and clay. So you can, there are the various approaches are there. So Meyer approach, Tazaki's approach, then your basic Hansen. So you can use any of them and calculate the static factor of safety for sand or clay. Okay. So so before I go to the example problem, so one more information I want to give also, that you can see this is the two curves. These are proposed by Bollinger and Idris in that 2004 report, that the magnitude of earthquake, if it is 7.5, then your number of stress cycle is 15 actually, because for sand like soil it is 15, you can see, but for clay it is not 15. You can see for 7.5 clay it is 10, 20, 30, around 32. So if it is the number of uniform stress cycle, if your tau average is equal to 0.65 tau max, then the number of uniform stress cycle in clay is almost more than double as compared to the number of uniform stress cycle of sand if for magnitude of earthquake 7.5. For magnitude of earthquake 7.5. You can see, you can check for another one. See, if it is 8, it will be around 30. But for sand, for clay, it will be around your 20, 30, 40, around 45, 46. So it is again, so that value will be, this is 10, 20, around less than 30 actually, 28, 27. Because I have given those expressions for Sidri's proposal, and that I have given the curve to calculate the number of equivalent stress cycle for sand. But for clay, it is almost double. If it is your magnitude of tau average is 0.65 of tau max, so it is more. So you can see for this chart that for 7, this if it is 0.65, this 0.65 is here, then it is almost double. Okay, if it is say 0.5, this is 0.5. If I take the tau average is 0.5, 50% of tau max, then this difference will further increase. The number of uniform stress cycle for sand and clay will further increase. But if it is less than this value, this is 7.5. Okay. So if it is less than or greater than less than 7.5, so that means if the tau average is less than 75% of tau max, then the number of uniform stress cycle is clay is more than the number of uniform stress cycle in sand. But if the tau average is greater than 0.75 times of tau max, then number of uniform stress cycle is sand is more than the number of uniform stress cycle is clay, in clay. That you can see. that is, it is greater than 0.75, then sand is more compared to the clay, but it is less than 0.75, then clay is more than the sand. And as we use for our case, we are using 65%, that is generally normally considered. So in that case, the number of uniform stress cycle of clay is more than the number of uniform stress cycle of sand. Clear? And it is, you can see it is for almost double. So in the next class, I will solve one numerical problem, okay, to show you how we can check the cyclic mobility, cyclic softening for clay-like soils, and to check whether the failure will occur or not. Or two cases I will consider. One is the free field without any building load, another considering the building load. Thank you.